The Rideau Canal, a staple of Ottawa's winter tourism and event schedule. Every year it sports thousands and thousands of kilograms of skaters, structures, and machinery. But do we ever think about what lies beneath our feet? Do we ever stop to consider what leads to the layer of ice we skate on every winter? How that ice forms? As we all know by now, ice forms by removing heat from water. But we must also consider where that heat goes. In the case of the canal, the main heat sink is the cold atmosphere above the surface of the water. In most liquids, density increases as temperature decreases. So as heat is removed from the surface, the cool liquid on top sinks to the bottom, and the warm liquid on the bottom rises, creating a cycle that cools the liquid evenly. In addition, when freezing, most solid states are denser than their liquid states, meaning that solids will begin forming at the bottom and grow upwards. Water behaves differently than most liquids, reaching its maximum density at 4 degrees Celsius. So below that, water cooled at the top will continue to be cooled and begin to form ice, which in turn will be less dense than water, floating on top and growing downwards. The next question becomes, if all that is needed to freeze ice is loss of heat, then why don't lakes, rivers, and canals freeze solid? What is the limiting factor of ice growth? The two main things that change as ice grows are the pressure that the freezing water is under and the thickness of the ice that the heat must pass through. Looking at the freezing temperatures in relation to pressure, we find this relation. So observing a stretch of canal near Carleton which is 8 meters deep, and assuming standard pressure at the surface, we see the freezing point varies by about 1 degree from top to bottom. Thus, pressure is not really a limiting factor of ice growth. Using the formulas for heat loss of a freezing substance and transmission of heat through an insulator, we obtain a function of thickness in relation to external temperature and time. Looking at this formula, we see, over a given period of constant temperature, the ice thickness grows at a rate proportional to the square root of time. So, back to the section of the canal. If a 1-day period freezes the canal to 1 meter thickness, it would take an additional 63 days for similar conditions to freeze the canal solid. Thus, the ice itself, as a thermal insulator, is the limiting factor of its own growth. When ice melts, however, it is the ice on top that turns into water. This water on top is denser than the ice below it and will find its way beneath the ice, leaving only a thin layer of water on top that the heat from the surroundings must penetrate to melt the ice. Applying the same equations again, we will see ice will melt in a roughly linear fashion, shrinking from the bottom. This provides a good clue as to why it is so hard to maintain ice. For the case of the canal section, if we observe a 1-day period that melts 1 meter from, say, 7 meters to 6 meters, then this will undo the work done by 13 days of freezing defined in the last example. This model is incomplete, however, and more investigating into freeze-thaw cycles is required for a better understanding.
The Rideau Canal is subjected to freeze-thaw cycles. Freeze-thaw cycles are defined as the weathering of a system due to the freezing and thawing of ice. A cycle is defined as one period of thawing and one period of cooling. When the temperature fluctuates around a temperature of about 0 degrees Celsius, we call this the threshold temperature. In Ottawa, it happens to be 0 degrees Celsius. However, this range can vary slightly depending on your latitude. Above 0 degrees Celsius, the canal will experience thawing, and below it will experience freezing. These fluctuations in temperature can cause the canal to expand and contract. This expansion and contraction causes the canal to crack, and in addition to the slush formed during these cycles, it can be hazardous to skaters. The damage caused by these freeze-thaw cycles is mainly dependent upon the intensity and the frequency at which these freeze-thaw cycles occur. The amount at which the ice melts during the thawing of the cycles is mainly dependent upon two properties of the ice. The first being the coefficient of volume expansion. If we look at the coefficient of volume expansion, and specifically if we take a look at the strip of canal beside me, if we assume that the water depth is 2 meters deep, and we take a 10-meter wide segment by 10 meters long, we can estimate that the volume of water is about 200,000 meters cubed. If we assume, just for the sake of argument, that 10% of that water is turned to ice, we can then find the fractional change in the volume for a 5 degrees Celsius change in the canal to be about 5 times 10 to the negative 8 meters cubed. Another property of these freeze-thaw cycles that comes into play is a phase change. So as the ice begins to thaw, it goes from solid to slush to water, and this can be specifically defined by the latent heat of fusion and by the specific heat capacity of water. Also, due to climate change, the overall global temperatures will increase, causing an increase in these freeze-thaw cycles due to more periods of warming during the typically cool winters.
The quality of the ice on the canal is maintained by the National Capital Commission. This is done by the strategic flooding and grooming of the ice in various sectors of the canal. The ice is cleared and flooded daily to ensure it is as safe as possible. This maintenance is done in sections to make sure that each area of the 7-kilometer canal is up to par. First, the section is cleared of both snow and other debris. This keeps the ice surface as exposed as possible. Next, the section is flooded. The flooding of the section fills any cracks or divots that may have formed throughout the use of the section and helps keep the ice from having fault lines. This allows the ice to refreeze and be reused by the public. It is possible that ice could begin to degrade and certain areas can be closed before others. This is due to their particular depth or because of their overuse from the public. If the area does not have at least 12 inches of ice, it is deemed unsafe by the Commission. During warm points of the season, it is possible that all of the canal can be closed temporarily. This is usually when the weather is projected above 0 degrees Celsius for multiple days in a row. The ice softens greatly when it is not kept below freezing point, and therefore becomes very unsafe for people to skate on. Once we approach the spring season and weather forecasts do not anticipate temperatures which would allow large portions of the canal to refreeze, it is closed to the public. The longest season, so far, was in 2005, with the canal open to the public for 66 days, and the shortest season on record was 2 years ago, where there were only 18 days open to the public for skating.
Every year around mid of January, that's when the temperature go really low and the canals start freeze and become a solid ice. When water begins to freeze on the Rideau Canal, it may look solid, but it's often dangerous. That's because of the thickness of the ice are lower than supposed to be. According to the NCC, there needs to be about 10 days of minus 10 Celsius of weather to get to the 30 centimeter of ice that's required to let people into the canal. During the winter season, we often heard about how canal closed for a few days and then reopen again. That's because of the temperature goes up and down. When the temperature goes up, obviously the ice gets melted. That's when the Rideau Canal closed down, and they wait until goes back to the minus 10, and then they reopen the canal, and also they make sure they check the thickness of the ice has to be about 30 centimeter. The Rideau Canals is a good example of how thermodynamic is involved during the winter and fall season, also the summer season. This is my end of presentation, and thank you.